going to demonstrate how to precisely measure the m-squared of a laser using the Haas Laser Technologies beam analyzer camera and beam waste analyzer cameras. Here we have the Haas beam waste analyzer camera that I'm going to put into our setup that already has our beam analyzer camera looking at the first surface reflection from a dove prism. The light passing through the dove prism goes through a focusing lens and then into the beam waste analyzer camera. One advantage to the Haas system is that there are no moving parts in this measurement, so the m-squared once measured is instantaneous. And let me just graphically show on this board here what this setup is. So we have our laser beam, in this case a helium neon laser, into a dove prism where the first surface reflection is directed into the beam analyzer camera, less than 1%, where we're measuring the raw beam diameter profile of the helium neon laser, and then the light coming out of the dove prism passes through a 100mm focal length lens and then into our beam waste analyzer camera that optically slices up the beam through the beam waste and simultaneously puts those images onto the sensor for an immediate measurement of the m-squared. I will now turn on the software and make a few adjustments. The camera is factory aligned, but there's probably a few adjustments that have to be made. Hit the play button, and I need to go to the frame grabber and look at the beam waste analyzer camera. So here we see the various spatial time slices, time delayed spatial slices of the beam waste, and I need to do a little bit of adjustment here to get it on the screen, which I'll do right here. And the other adjustment to get a few more spots on the screen. All right. So the important thing is that we just get we have about 11 spots within our main region of interest here. So this is showing the beam waste time slices of this beam. So now, as we go to the summary screen here, we've got our profile, which is measuring the raw laser beam. And then we've got the BWA-CAM measuring the spatial time slices through the beam waste. So now we can go to the m-squared screen, and here we have an immediate measurement of the m-squared. We've got just a little over 1, which is correct for this type of laser. It's a very Gaussian beam. And we have a beam waste diameter of about 84 microns for this 100mm focus lens. One advantage to this system is we get m-squared instantaneously. So if I block the beam with this business card here, see, we have no longer a beam caustic, and I put it in, the m-squared is instantaneous. The dual camera mode software gives a variety of features here. We have, of course, our raw beam profile measured before the lens, our actual beam waste measurement, and then, of course, we have the quality control capability where we can display whichever ISO standards parameters that we want for the profile or for the m-squared values. Here I have astigmatism, the m-squared for 2-camera mode, that means BA, BWA, or single camera mode, because the camera itself is capable of measuring the m-squared, but not quite as precisely as the dual camera. This, with the BWA-CAM, is probably accurate to within 10%. The dual camera is better than a few percent. And here we have Rayleigh range and the beam waste position for this given focus lens. Now we have, of course, our frame grabber screen for either camera that we can see. Then we have our surface plot for the profile camera. It's not available for the beam waste analyzer. Then we've got our 2D plot of our profile. We have our logging screen where we can log all the data for both cameras by clicking the Start button, the beam waist diameter, which is about 85 microns on the average for both axes. And as well, we can log this data to a file, or we can print out any of these charts as a PDF file. We have here our quality control screen where we can set the parameters that we want to track either as the beam waist or as the raw profile. A red means it's out of specification or out of the limits that have been set. And of course we have our M² screen where we can enter the laser properties. Say if we're measuring the values of lasers coming off a manufacturing line, we can put in all the information here to designate that laser. We have the settings where we enter our focusing lens. We have our actual beam waist caustic. We can create a report of this M² measurement. So we have the beam waist caustic as well as the basic data for the beam waist measurement. And the beam waist analyzer camera itself can be calibrated for the spacing between the Fabry-Perot etalons inside that allow the spatial time slicing of the beam. That's a very simple procedure. And of course we can get an image statistic report which shows the image for both cameras along with the beam waist caustic and the data measured by the camera. So the way the Haas Laser Technologies beam waist analyzer camera works is, some of you may be familiar with a Fabry-Perot interferometer. Our system looks optically very similar, except that instead of the light coming from this side, we come from this side. So from the lens side into the Fabry-Perot etalon pair. So that we see this here, we have our focusing lens, our beam coming in, we've got our etalon pair, and the light, a small portion of light passes through, but a lot of it gets trapped between the two etalons so that we get a time slice of the beam. So here we have our first beam coming through, a very small percentage passes through, and then we get reflection of the beam being displaced laterally and then re-emerging with that time delay between the spacings of these two mirrors by this value here. When we get here to this graphic, we see these spatial time slices of the beam throughout the beam waist, and this is what's superimposed onto the camera sensor so that we can see the entire beam waist in one image. So what makes the Haas Laser Technologies beam waist analyzer camera different from other M² measurement systems on the market is that we have no moving parts. In other words, we don't have to move a lens, we don't have to move a sensor, we don't have some spinning component like an aperture or slit or spinning needle. Many of those devices can require minutes to take the measurement. We do it in a fraction of a second because all these spatial time slices through the beam waist are superimposed on the sensor at one time. So it's an instantaneous measurement.